Hi again. As we were discussing the topic of surface tension, we mentioned that it's good to actually apply some of these principles on a simple example. I'm bringing again the example that we did in one of the recitations, the puddle example, but just to reemphasize and kind of refresh your memory on the very basic concept that whenever you have these surface tension problems, very much like any other problem in fluid mechanics, you can derive a certain contour volume around the area of interest or the region of interest in your problem. And when you draw a contour volume, everything will be very similar to what we have done before. The only thing you need to keep in mind, if your contour volume cuts the interface between liquid and air at certain points or lines, don't forget the line force that you have there due to the action of surface tension. For example, here in the puddle problem, the contour volume I have drawn is the dashed green line, which is forming a kind of a rectangle here. And I can see that I'm cutting the interface between liquid and air at one point here. So parallel to the interface between liquid and air, which is parallel to the surface of water, I should have a surface tension force, which is a line force I denoted by F of sigma. I'm also cutting the interface between liquid and air at another point. So again, parallel to the interface, I should put an F of sigma. And this line, we know that it's making an angle equal to alpha, which is set by the contact angle of water on this substrate that we have in the problem. And we found that actually these are not the only two forces acting on this contour volume. There is also another force that can give us horizontal component for force, and that's the pressure, hydrostatic pressure distribution we have in the puddle due to the weight of the fluid elements. So that would be pressure as a function of y that forms, if we take the contribution of ambient away, forms a triangular distribution, and we can easily calculate the net force of that. If you write down the balance of forces in this problem and the x component of that, we can easily find an expression for the height. And we notice that in many of these problems, when you have the balance between gravitational forces and surface tension or capillary forces on the other side, you find this nice scaling that length scales become proportional to one thing that we called, so h in this problem becomes proportional to L of c with some correction that comes from the contact angle. You can go through the recitation video and remind yourself what was that correction parameter, but they become usually proportional to L of c, which L of c is the capillary length scale, and by definition is defined as the square root of surface tension, which is sigma, divided by rho g. This is a length scale that naturally comes out of the balance between gravitational forces and capillary forces. And for objects below this length scale, surface tension is a dominant effect. And for objects larger than this length scale, gravitational effects or body forces are the dominant factor. That's why we use this length scale in our definition of bond number, and bond number is indeed the length scale of the object or the geometrical feature that is given to us, r, divided by capillary length LC to the power of 2, which if you write terms, it simplifies to rho g r squared divided by sigma. Again, you clearly see that this number that we defined, which in many static problems that are involved with surface tension, it naturally emerges. There is a contribution from density, gravity, your length scale of the geometry, such as, for example, body size, my diameter of my body, r, and surface tension, sigma. There are multiple ways you can make a problem go to limit of low bond numbers much smaller than 1, or there are many other ways you can go to the other limit, which is bond numbers much larger than 1. And you can clearly see here capillarity wins, and here body forces or body force wins when bond number is much larger than 1. That's why a water strider can stay on the pool in a very easy manner thanks to surface tension forces, but humans, our weight and our length scale does not allow that to happen. This is all the discussion that we have had so far. All are based on, for example, what value of g we put here. On planet Earth, you can calculate, for example, capillary length scale, and it becomes approximately equal to 2.7 millimeter using the gravitational constant we have on planet Earth. When you go to a space station and you have much smaller values for g, you can easily see that your capillary length scale becomes much larger than what we have on this planet. So for many objects much larger than water strider and even objects of human size, on a space station or microgravity conditions, they may have a bond number that would be much smaller than 1. That's why in many space applications, effects of capillarity and surface tension are not negligible. They are important, even up to sizes much larger than what conventionally we are used to think of on our own planet Earth. That's one topic to keep in mind. The other thing that we discussed is sometimes you have motion, and within the motion you have deformation rates and viscous stresses or inertial stresses. And if in the problem is not static anymore, you have motion, you have a dynamic problem, and the effect of surface tension is also involved, then you need to compare the scale of these viscous terms or inertial terms with respect to the corresponding scale for capillary or surface tension forces. And if you do that, in the lectures we have shown, you develop certain new dimensionless numbers. So, for example, here what we discussed can be considered important for many static problems, because the puddle is not moving, the drop is not moving. These are usually called static problems. But if you have dynamic problems, then you form certain dynamic dimensionless groups. And I just write down a list of these groups to refresh your memory. If you compare viscous stresses with capillary, you get what is called as capillary number, which is defined as viscosity multiplied to velocity divided by surface tension sigma. And this is, as I said, called capillary number. Similarly, you can compare the scale of inertial terms. So let's say inertia terms divided by capillary. And if you do that, you get what is known as Weber number, which is defined as rho v squared multiplied to r divided by sigma. One way you can always check is really unitless and dimensionless. Rho v squared is a pressure. Sigma over r is also a pressure. So rho v squared times r over sigma is a dimensionless group that really compares the scale of pressures or stresses related to inertia, which are captured by rho v squared term, compares that to other stresses that you may have in your problem that are coming from surface tension or capillary nature, and those usually scaled with sigma over r. You also have seen that in some other problems you can have certain time scales or things that are important, such as, for example, the time scale, Rayleigh time scale for vibration of a droplet. And we notice that in that vibration process, the inertia of the liquid and the capillary are usually in balance with each other. So if you have a droplet, a spherical droplet with radius r that is vibrating, it has a certain inertia, and the resisting or the spring constant comes from the surface tension, and that gives rise to a vibration process with a certain period that is proportional to what we call Rayleigh time scale, which goes as a square root of rho r cubed over sigma. Again, to check that this has indeed a unit of time, you can easily check it. Let's take, for example, t squared, and that would be rho r3 over sigma. And you can easily see that if you bring t squared under r squared, it will be rho r squared over t squared, which is a rho times velocity squared. That's pressure. And then you will be left with a sigma over r, which gives you another pressure. So again, you can always check and make sure that indeed this has unit of time or second. And we calculated this for, in the lectures you have seen, for jets or droplets that are very small. And you saw that this number, this Rayleigh time scale, which says the vibration time scale of droplets or jets, can be of order of very small values, milli or microseconds, depending on the size of a jet. And that's why when you open a tap of water, you may not notice the phenomena of the jet breakup as it transforms from a uniform or cylinder or a column into individual droplets. That process happens so fast, this time scale is so small that you need to use high-speed camera or advanced flash photography techniques to be able to visualize the vibration process. But nevertheless, it happens, and it happens in this time scale. And we notice that for the vibration or fluctuations that we have, which have this kind of balance between inertia and capillary, if viscous stresses are also present, and if we want to find whether they are important or not, we can use the definition of this number, Ohnesorger number, which is the ratio of viscosity divided by a square root of rho multiplied to surface tension sigma multiplied to length scale r. And we mentioned that this Ohnesorger number, which is named after a German engineer and scientist, Ohnesorger, has a significant meaning. It is the ratio of viscous stresses or viscous time scale over the inertia capillary time scale that you have in this jet or droplet breakup phenomena. In some ways, if you think about a balance of energy, as you have a conversion of energy from inertia to capillary and vice versa, if you had some viscous damping effect and the energy was dissipated through this viscous damper or damping mechanism, the energy level of that viscous damping phenomena made dimensionless over the kinetic energy or capillary energy would give you this ratio, and this ratio naturally comes out of there. We have done this in the lectures. I'm just mentioning them again so that you keep this fresh in your mind. And you can actually go and calculate, for example, for water, a jet of water, a droplet of water with a viscosity 1 millipascal second and a certain radius of, for example, a millimeter or a fraction of a millimeter, and a given surface tension and density, what values of Ohnesorger number you measure. You can clearly see that when Ohnesorger number is much smaller than 1, you don't need to worry about viscous effects because viscosity is in the, on the top in the numerator. But if the Ohnesorger number becomes larger and larger, you actually have to really be concerned about viscous effects. And as you see from this expression, as the radius of the jet or droplet goes to small values, as it goes to micron-sized droplets or jets, Ohnesorger number increases because it goes as 1 over the square root of r, or length scale. And that's why for very tiny microfluidic applications, droplets or jets, ink jets, or other processes where we deal with micron-sized droplets, we cannot really ignore viscous stresses easily because you may indeed have a relatively large value for Ohnesorger number. This was an overall review of the topic of surface tension. In the next video, we will do a simple problem that has a combination of some of these concepts together, and we show how you can actually mix these ideas together and address a relatively interesting and important problem that we will describe in the next video.